Okay, I just unmute myself. Okay, so can you see the slide?
Yeah.
Okay, hello everyone. I'm Kunpeng from Learning Algorithms and Systems. Okay, sorry. From Learning Algorithms and Systems Laboratory, EPFL. I'm glad to share our study on how the task complexity affects the human's control of hand poses in bimanual fine manipulation tasks. Robots are able to perform bimanual tasks by learning from human demonstration. Nevertheless, human bimanual dexterity remains unattainable for robots despite the large amount of degreed freedoms that need to be controlled. Humans select hand poses according to task conditions, such as the task goals or objects to be manipulated. So understanding human hand control strategies inspires the design of robot control and learning algorithms. We study human watchmaking craftsmanship as it involves the coordination of fingers that results in abundant hand poses to perform the task. We focus on the unscrewing of a watch screw. It requires using a slot-head screwdriver to dismount a tiny screw from the watch face. Subjects have to rotate the screwdriver while maintaining a pressure to avoid sliding. And task demands can be reviewed by the signal recorded from the force torque sensor mounted underneath the watch face. We design two experimental conditions based on if the watch face can be moved or it is fixed on the table. And the difference in task conditions results in different number of the degrees of freedom to be controlled. And for each observed hand pose used by human subjects, we first analyze the assignment of virtual fingers. Each virtual finger may consist of one or more fingers or part of the hand that move in conjunction and apply same forces as one real finger. So for example, this observed hand pose, it has three virtual fingers. And if we observe the force torque signals in task relevant directions, we assert that this hand pose has the ability to generate a task demanded force or torque. And we summarize all the observed combinations of the left hand and right hand poses for each experimental condition. So in the difficult case with the moving base, we see barely variability in the solution. And matrix entries indicates the total number of trials in which this combination was observed. Subjects use dominant hand to manipulate the screwdriver while the other hand to control the watch face. Now consider the case with fixed base. Since the base no longer needs to be controlled, we expect subjects use only the dominant hand to perform the task. But interestingly, we see large variation in the solution. So why would humans use two hands if they can complete the task with one single hand? So if we check the assignment of virtual fingers for each hand pose, we see that in the moving base condition, the dominant hand pose have three virtual fingers, enabling them to control for both torque and force simultaneously. The system hand can only compensate the perturbation. In the fixed base case, we see that in most trials, the assignment of virtual fingers are divided between two hands. So one virtual finger from one hand to control force, and two virtual fingers from the other hand to control torque. So this decoupling of force and torque control was observed in 80% trials, and it is achieved by decentralizing the assignment of virtual fingers between hands. So to conclude, we show that humans decouple the control of independent task demands by decentralizing the assignment of virtual fingers between hands, and it informs the design of robot control and learning algorithms that simplify the robot control. Thanks for your attention, and please refer to the project website for more information.